wait all day for these people. Hey, Haley, are you paying attention? Hey. A function y equals f of x is differentiable in a closed interval if the right-hand limit and the left-hand limit of the derivative, so the right-hand derivative and the left-hand derivative, exist at the endpoints. We've seen this before, I think. So it's just basically saying that as long as, if we're going to an endpoint, just close the door.
Close the door myself.
Well done, Samantha. Okay, so looking at an example here, for the derivative to actually exist at a place, the left-hand limit for the derivative must equal the right-hand limit. What that really means is just that the derivative must be equal on both the left and the right side. Oh, there's all this writing on the board. So if we're looking at one like this, this is a piecewise function. At x equals 0, we have the two pieces meeting. We can see from the picture that it's continuous, but not necessarily differentiable. Thank you, Lauren. Okay, so if we look at this example, if we want to show that the derivative doesn't exist here, the way we would do it is we'd look at the derivative on the left and the derivative on the right. So from the left, and from the right, okay, and we would compare them. And for it to be differentiable and for it to have a derivative at the value 0, we would need to show that they're the same. So the left derivative, f prime of y, or y prime, I guess, y prime, because it's y here. So we've seen that notation where we call y, the derivative of y prime. And remember what we learned yesterday. So from the left, that would be the top equation, because that would be the left. So it's 2x, and remember what we learned yesterday, we dropped the power down, so the coefficient is going to be 2, because the power was 2, and it's going to be x to the power of what? 1, because it's 1 less. Okay, so y prime of the left derivative is 2x, and if I look at the right derivative, and I take the derivative of the right derivative, hi Olivia. Okay, the right derivative of 2x is what? What's the derivative of 2x? 2. Okay, now to check if they're the same, because obviously those aren't identical, but they could still be the same potentially at the value 0, you have to plug in 0. So y prime of 0 on the left is 0, because 2 times 0 is 0. And y prime of 0 on the right, what is 0 if I plug, or what is y prime if I plug 0 in for x there? 2, because there's no x. So since they're not equal to each other, y has no derivative at x equals 0. Okay, that's what we would say. So just to do like kind of a There's a few ways that a derivative might fail to exist, like we just saw. It's always when the left and the right derivative aren't equal for some reason, but there's a couple situations that happen a lot. A really typical one is a corner. You should know these words. I'm sure corner will be very hard for you to learn. But it's like this. It's when there's a corner. Okay, so it's like a pointy part where they meet, like in an absolute value function. That's a corner. And so if you were asked a question like, why is something not differentiable at this point, you would say, oh, because it has a corner there. And that's fine. That's like actually the terminology you would use. However, there's other things as well. So another thing is a cusp. Okay, so this is a cusp, not a corner. I don't like it when people call things that are cusps corners, so try not to. So you can see it doesn't look the same as a corner. The lines on both ends are curved. Okay, a corner is something that you get with straight lines. Okay, so this is not a corner. It's called a cusp, but it's the same situation. We wouldn't have a derivative there because the left side would be negative, the right side would be positive. Okay, a vertical tangent. So here on this example, which would be the cube root of x, you can see that there'd be a vertical tangent line at 0. Where there'd be a vertical tangent line, we just say that the derivative doesn't exist because it would be undefined, right? It would be infinity, which is undefined. So we can't say what it is. It's because it's coming positive from the right, the left, and negative from the right. So a vertical tangent line is considered a derivative not existing. And finally, if you have a discontinuity. So if there's a discontinuity, it's just really important that you understand that discontinuity automatically means no derivative. Okay, so any kind of discontinuity. Okay, so it could be a discontinuity like a jump discontinuity like this one. It could be an infinite discontinuity. It could be just a removable discontinuity. No matter what type of discontinuity we have, we will see that the derivative doesn't exist. Okay, so we're going to work through some of this together here. Thank you. Yes. Okay, so we are going to go through this sheet together. Yes. I guess I should. Okay. Okay, guys. So we talked about continuity already, and so we don't need to look at it too much, I don't think, here, but we will kind of review it. So remember that the definition of continuity happens when, and it says here, it kind of really breaks it down, if the limit at c exists, the function at c exists, and they are equal to each other. Okay, so we've seen that before, that the limit and the function must both be equal to each other at a value c for it to be considered continuous at c. So if we look at these examples down here, okay, we are just supposed to be saying if they are continuous at c, and if not, say which of the rules it breaks. So is a continuous? No. Okay, it's pretty clearly not continuous. Which rule does that break? Does it break 1, 2, or 3? Because 1 is that the limit exists, 2 is that the function exists, and 3 is that they're equal to each other. It breaks number 1. So it breaks number 1 first, anyway. It also would necessarily break number 3, because if the limit doesn't exist, it can't. But the issue is that there is no limit. The limit from the left and the limit from the right are not equal to each other. So there is no limit, so that means it can't be continuous. Okay, now the second one, is that one continuous at 1? No, because it has a removable discontinuity there. Okay, this is stuff we all know. Now that one, does it have a limit?
Yes.
Yes. Does f of c, which in this case would be f of 1, does f of 1 exist? No, so it breaks number 2. Okay, c. Question C there, is that continuous at 0? No. Does that have a limit at 0? Does it have the function existing at 0?
Yes.
Yes. Are they equal to each other?
No.
No. That's the problem there. The limit would be equal to, I don't know what the value is there, it looks like maybe 1. Okay, so the limit would be equal to 1. The function would be equal to -1. They're not equal to one another. That's why we have a problem there. D, at 4, is it continuous?
Yes.
Yeah, there's no problem with that one. Okay, number E, is that continuous?
No.
No. Does the limit exist? No, the right and left limits are different. Okay, F, is that continuous?
No.
No, and again, the limits don't exist. What about G? Yes. Okay, and H is again no. Okay, so we've seen this before. It's just refresher because we're now going to be looking at differentiability. Differentiability and continuity are really related. I want to go over just a couple of these questions again because some people had some problems with them on the test. So we're not going to do every single one of them. I'm not interested in doing that, but we will look at a couple. So example 3 here, if we're looking at if a piecewise function is continuous, the way you do it is you look at the value that is where they switch. So for this one, I'd be looking at the value x equals 1, and you'd be looking at the left-handed limit and the right-handed limit. So if I'm looking at the left-handed limit of f of x, if I'm looking at the left-handed limit of 1 of f of x, which function would I be looking at? The bottom one. It's a little out of order. So I'd be looking at the bottom one, so I would do 1 minus x, and I'd plug 1 in for x. So I'd get 1 minus 1, which is 0. Then I would do the right-handed limit, and this was on your assignment, something basically exactly like this. Okay. The right-handed limit of f of x, I would look at the top function, and what would I do? Put 1 in, so I get 1 squared minus 3, which is? -2. So this is not continuous because the limit doesn't even exist. Okay? So the limit needs to exist, and it needs to be equal to the function itself. Okay, that's the two requirements that have to be met. Okay, so let's look at one of these because this was on the test, and some people did not get them right. So here, if we need to find a value k that will make this continuous, okay, we want to make it so that the left limit is equal to the right limit. So I can see here that the right limit, in this case it's a little different because there's only one k. The one on the test had 2 values. But if I was doing the right limit here of f of x, it would be the top function, so it would be 5. I need to figure out a way to make the bottom function equal to 5 as well. So the way I do that is I take 2k minus x and I set it equal to 5. I think most people got this and understood this part, that they needed to set them equal to each other, but people didn't know what to put in for x. So since I'm actually not just setting this equal to 5, I'm setting the limit as x approaches 1 equal to 5. So I have to plug 1 in for x. So I get 2k minus 1 equals 5. So k is 3 in that case. If k was 3, these functions would be continuous. Okay, that's how you do them. So this one, let's just do one more. Okay, I would plug 2 in for k right away. I wouldn't actually think it all out the way that, I wouldn't be really slow. I would personally plug 2 in for k right away. So the right limit would become 4k. And the left limit would become 2k minus 6. Okay, so all I did was I plugged 2 in for each of those x's, okay, and I wrote them down and I made them equal. Because for it to be continuous, they have to be equal to one another. Okay, then I end up getting k equals -3. Okay, just doing a little bit of algebra. Okay, so there was one like that on the test and on the practice test. And people had varying levels of success with it. Okay, so I know a lot of people did it on the practice test but couldn't do it on the real test. So I don't know why, but that's life. Okay, so that's all old. Now we're going to get into differentiability. Okay, so something is differentiable if and only if f prime exists. That makes sense. And f prime has to be a real number. So f prime can't be infinity. That's what it's trying to say there. If you think the derivative is infinity, what you say is it doesn't exist. Okay, so that means that those vertical tangent lines is it not existing. Okay, on an interval, we would say it's differentiable only if it's differentiable for every value on the interval. And a function, oh my god, this is the same terrible definition. But anyway, a function f of x is differentiable if and only if it's differentiable at every value of x in its domain. So differentiable, and it says here in layman's terms, you could consider it to mean smooth. Okay, there's no sharp edges, there's no cusps or corners, there's nothing that makes a vertical tangent line. Now, there's some stuff you really have to know in this bottom box here. Differentiability, if something is differentiable, it must be continuous. Okay? If there's a discontinuity, there is no derivative. So if it says a function f is differentiable, it means it's also continuous. Okay? It has to be both. Okay? However, it doesn't work the other way. Continuous does not mean differentiable. Okay? So differentiable does mean continuous, but continuous does not mean differentiable. The reason for that is because a corner, you think about a corner, is continuous, but it's not differentiable. So you can have a graph that is continuous, but not differentiable. You cannot have a graph that is differentiable, but not continuous. Okay, there's no such thing. Hey, Clayton, you have a question?
Could it be, like, is it a corner at any angle, or is it a right angle?
No, any angle. As long as the lines on either side of it are straight.
Okay.
Okay, that's a good question. Okay, so so if a function isn't continuous, it automatically can't be differentiable there. So now we're going to say same functions for the most, these are actually the same functions. We're just going to state if they are continuous, differentiable, or neither. Okay, so this first one, we've already said it's not continuous. Is it differentiable?
It's not continuous.
It's not continuous, so is it differentiable? No. If it's not continuous, it's automatically not differentiable. Okay, so let's just put x's, or I guess it's neither then. It's neither. So we'll write n for neither. Okay, the next one, is it continuous? No. So is it differentiable? No. So if the first answer is no, the second answer also has to be no. Okay, the third graph there, it's different than the last page. Is that continuous?
Yes.
Would it be differentiable?
Yes.
Yeah, it's both. Okay, so at the top there, there's no corner or anything. Okay, so it's differentiable. At the very top of that, the tangent line would be horizontal, so it would have a slope of 0. But that's fine. Horizontal lines are fine. It's vertical lines that aren't fine. Clayton, you have another question?
Would you mind quickly re-going over if the function's continuous, what are the characteristics that wouldn't make it differentiable?
If there's a cusp, a corner, or a vertical tangent line.
Okay.
Okay? So if it has that cusp or corner, which is kind of the same thing, they're not exactly the same, but they look pretty similar. Yeah, they look pretty similar. Cusp or corner, and then also if they have a vertical tangent line.
Okay.
Okay? So D is continuous. Is it differentiable?
Yes.
No.
Someone who said no, why do they think it isn't?
Looks like it's not, doesn't look like the other one, like smooth like this.
Yeah, it's not smooth. That circle right there, that is a corner or a cusp. I don't know which, to be honest. It's one or the other.
Nice that corners had to have two straight lines.
Yeah, so then let's call it a cusp. Okay? But either way, there's something there. From on the left side and the right side are not the same. There's like a weird sharp place, right? There's like somewhere that you'd have to take a sharp turn on. That means that it's not differentiable. So this one's only continuous because of that place. Okay, E, is that continuous? No, so this is neither. F, is it continuous?
Yeah.
Yes, is it differentiable? So it's just continuous. And again, that's very clearly a corner. Okay, the next one is that differentiable? Or, sorry, it is continuous, but it's not differentiable, you're right. Okay, because of that there. That's a cusp kind of thing. H, is that continuous?
Yes.
Yes, is it differentiable?
No.
It is not differentiable, why not?
It has a vertical tangent.
Yeah, it has a vertical tangent line, somewhere around there. So it's just continuous.
I get it.
It's a straight
Wait, so, oh, I see what you mean, you can't have that line.
Why did they let them have vertical lines?
Because that would be, the slope of it is undefined. Okay, I, okay guys, I there, x squared minus 6x plus 1, what would that graph look like? You have a question, Ryan?
For the vertical tangent line, is it like actually vertical?
Yeah.
So it's not a function?
No, it's like the cube root of x is a function, but it just has a point right in the middle where the tangent line would be vertical. But it doesn't mean the graph is vertical.
Okay, so it's not like an actual vertical line?
The graph is not an actual vertical line, the tangent line is.
Yeah.
Yeah. Okay? Okay, no, it's okay. I there, x squared minus 6x plus 1, what kind of graph would that be?
A linear, diagonal, straight line.
The derivative would be.
Yeah.
Yeah, the actual graph would be a parabola.
Yeah.
So you think of that, the parabola would be a smooth curve. Okay, also you can think of the derivative is linear, so it's going to always exist, right? So that one is both continuous and differentiable.
So do you, when you're trying to find it, it's differential, is it like based on like the derivative or the original?
Yeah, more the original. You could, if you know the derivative though, like, and you know the derivative is a function, then you know it's going to be, okay? X squared minus x minus 12 over x plus 3. That graph, is it going to be continuous?
No.
No, it's going to have a discontinuity. So if it has a discontinuity, can it be differentiable?
No.
No. So this one's neither. Sine x. Is sine x, the graph of sine x, continuous?
Yes.
Yes.
Yes, it's just a wave. Okay. Is it smooth?
Yes.
Yeah, so that's both.
Wouldn't there be a vertical tangent line at some point?
Not on a sine graph, because it's like this. Like, it's not ever, it never, like, completely like that. Okay. I know it's hard. It's sort of just a practice thing before you start to realize what a vertical tangent line looks like. But it's pretty clearly like a very steep fall. Okay. Sine x over x. I don't know if anyone remembers what that graph looks like. You remember?
Oh, I do.
Yeah.
Is it one?
That's the limit as x approaches 0. Yes. Okay. Which is actually good to know because that means the limit does exist there at 0. But it would also have a discontinuity at 0, right? Because sine 0 over 0 would cause a discontinuity. So this one would be neither, just because it would have a discontinuity. Okay, I'm just going to do like 1 or 2 of these with you, and then I'm going to give you guys some practice to do. Okay, so this one here, we are trying to decide if it's continuous and or differentiable where the function changes. So there's a little space there to graph it if you want. So if you wanted to kind of sketch the graph, you could. I know that this is going to look like at 2. My linear graph to the left would be at 2. How did I know that?
It says equal to 2.
Could you put 2 in for the bottom one?
I put 2 in for the bottom one. Thank you, Haley. Okay, so it's just going to be a line that's going down towards 2. If I plug 2 into the top one, I get 4 minus 6, 4 minus 12, which is negative 8 plus 10 is also 2. So that'll be a parabola starting at 2 and going up. So my drawing kind of sucks because the graph is like totally not in it, but it's fine. I can see though it's going to be a line on one side and a parabola on the other. Now to check, I mean it's clearly continuous because it connects. Now to check if it's differentiable though is actually a little trickier because sometimes you can have a situation where a linear graph connects to a parabola and it is differentiable. Like if you have like a really nice straight line that like kind of morphs just perfectly, smoothly, if you will, into the parabola, then you're going to have a differentiable function. So the way to check is you find the derivative on both the top and the bottom. So that derivative, x squared, the derivative of x squared is what?
2x.
Yep, everyone got it at the same time. Minus 6x becomes minus 6. So at 2, that value is negative 2. So that means that my parabola has a slope of, I just plugged in 2. Are people okay with that?
How'd you get negative 2?
I plugged in 2.
Oh, okay.
Okay? Then on the bottom, the derivative of 4 minus x. Does anyone have an idea of what the derivative of 4 minus x is? It's not 4.
Is it 3?
0.
Is it 3?
It's not 3.
What?
It's negative 1. So since negative 1 is not equal to negative 2, it is not differentiable. Okay, so the reason it's negative 1 is because there's a negative 1 in front of the x, and that's the coefficient. The derivative of 4 is 0. Okay, so that's how you do this. You check the derivative of the top and check the derivative of the bottom and see if they're equal to each other. Let's just do one more of those. I'll do the last one because it's probably the hardest. That's usually the way these things work. Okay, so again, if I was trying to sketch this, I would say, okay, so it's sine x for when x is greater than 0. So sine x looks like this, because I have it memorized. Okay, and x minus x squared, if I plug in 0 into that, I also get 0, which is great, because that means they are continuous. So it's definitely continuous, and that would be a parabola. It would be a negative parabola. I don't really know what it would look like there. I'd have to like actually graph it or do some values or something. I know it's going to go through 0, 0, 0. If I plug 1 into it, I get negative 2. Actually, no, I guess I shouldn't plug in 1. I should plug in negative 1. So if I plug in negative 1, I get negative 4. So that would be somewhere down here. So it seems like it's going down, which actually seems like it might be smooth. Okay, it kind of seems like it could be a smooth transition. So to check if it's going to be smooth, I take the derivative. Now we actually don't know the derivative of sine x yet, so I'll just tell you. If you see any trigonometric ones on this, just skip them for now, but it's pretty easy. The derivative of sine is cosine. Pretty tricky. Okay, so if I plug in 0 into that, I get, if I cosine 0, does anyone know what cosine 0 is? It is 1. Fantastic. You had a 50% chance and you nailed it. Okay, so the derivative of the next one is 1 minus 6x. So if I plug in 0 for it, I get 1. So since 1 does equal 1, it is differentiable. Okay? So that's how you do those questions. We're going to do one of these last ones because it's very similar to the ones that people sucked at on the test, except for now it has an extra aspect to it. Okay, so I'm just going to do one of them. I'll do this easier one. So it wants us to find the values of a and b, and I guarantee you there will be one of these on your test for this unit that make it both continuous and differentiable. Okay, so we want it to be both continuous and differentiable. So that means that we want them to equal each other at 1. So if I plug 1 into them, I get 1 squared times a, which is a, plus 1 equals b minus 3. If that's true, it'll be continuous. Now to make it differentiable, I need their derivatives to be equal to each other. So if I take the derivative of ax squared, what will I get?
2ax.
2ax, fantastic. So 2ax must equal, and if I take the derivative of the bottom there, does anyone know what that would be? Not 1. And I'm gonna let x equal 1. So I have 2a equals b. So I have two equations here, which is enough when I have two variables that I should be able to solve. So I can set it so that a equals b minus 4. Is everyone okay with that? Is everyone okay with that? I'm not hearing anything.
Yeah.
Yes? Okay. All I did was subtract 1 from both sides. Then I would plug that into a over there. This is called substitution. We have done it before. So I get 2b minus 8 equals b.
Oh, I'm sorry.
Which is b equals 8. And then I can set 8 over here. So a equals 8 minus 4. So a is 4. Okay? But it's a little bit more complicated now because we have two different equations. We have to use one of them to do substitution and the other. Or if you wanted to do elimination, I guess you could. It's probably not going to be easier though. And then you go back and forth and figure out what the two variables have to be in order to make this work. Okay, so does anyone have any questions about any part of that? Where something comes from? Nothing like that? Okay, I'm going to hand you out some problems that are